So let's start. I'm going to speak about some issues with MPI specific things and about collective operations. Before we have discussed about some send and receive operations, which are called as point-to-point operations. That means these operations are between just two processes, one process and another. But today we will discuss about collective operations where all processes are included in this discussion process. But before this, I'm going to start with, for example, deadlock. This is a specific thing which maybe you were encountered with in your program. What does it mean? Suppose there are two processes, process 1 and process 2, and they want to exchange the data. If you write like this, so firstly MPI process number 1 try to send something and process number 2 do the same. So it also wants to send something firstly. So MPI send, MPI send. These operations, MPI send and MPI receive, are blocking operations or synchronize operations. That means if some process run this function MPI send, it will blocked until process on the other side will receive this operation. Remember? In this case, all these two processes will stop their function, their operations on these functions, and by the way, will never continue their work because, for example, process 1 tried to send something and stopped. It will continue only when process number 2 will run MPI receive operation. But it will never do this because it also, in a stop position, it will frozen onto this in this line because process number 1 will never run this function because it is frozen onto this line.
So how is it going to work? First MPI send, it's going to receive in process 2, and then process 2 is going to send to process 1. Or do they send simultaneously?
Yes.
Same time.
So on the logical way, on time level, these two operations, MPI send in process number 1 and MPI send in process number 1, are on the same level, on the same logical and time level. In this case, they will never send and they will never receive some messages. That means your program will be frozen and so on. So this is a classic deadlock. So what is the solving of this issue? So firstly, you can change the order of operations. For example, if you change the order of operations in the process number 1, so process number 1 firstly will receive and secondly will send, that means all will be okay, because process number 2 will try to send and process number 1 will receive this message. After that, it will continue its operations, its work, and will try to send message to process number 2. and process number 2 will receive this message because it will not be blocked at this position. Okay? So, what is the conclusion? On the same logical level or time level, it's up to you, should be in one process send operation, and always on the other side in the other process should be receive. So on the logical level should be send, receive, or receive, send, and so on. If you will write so, you will never encounter with a deadlock. Okay? So let's see this in a code. For example, so you can see here some MPI code, and you can see rank number 0 has two variables, A and B. A equals to 0 as its rank, and B equals to 10, and the last digit as a rank equals to its rank. In process number 1, A equals to 1 as a rank, and B is 11, so the last digit as rank. So just to recognize, using variables, we can recognize the rank of the process, just for simplicity, for convenience. So you can see process number 0, okay, let it be, tries to send something to process number 1. You can see it tries to send A to process number 1, and let it be here. And process number 1 also wants to send something, I mean A, in process number to process number 0. After that, it wants to receive B. Okay, in B, so all these processes will send A, but will write the information in B. Doesn't matter.
So this creates a deadlock.
Yes, we'll see. Will it work or not? And every process will print some information, N and B. So A will be, if there is a process number 0, A will be 0, and if nothing happens, B equals to 10. But if the exchanging, will be an exchange of information in 0 process, B will be 1, and in process number 1, B will be 0, something like this. Okay, we'll see. Okay, open, no. Wait. Open API 4. Where I am. Collective. So you can see, if there is a 0 process, A equals to 0, B equals to 1. So the exchange occurs if there is a situation of deadlock. one a minute. But if we make the order where firstly they try to receive something, there is yes, but so I just stop. So you can see that this is almost the same situation as it was when firstly there were two send functions. Here you can see there are two receive functions firstly, and there is a deadlock. But by the way, if there is firstly send, it also should be a deadlock.
Yeah, but the thing in the send, as you showed in the previous graph, they try to go diagonally, and it might work.
No. So deadlock should be in all two cases, but we can see that it is just in one case, and in this situation there is no any deadlock. So this is some confusing point here, because this function, okay, MPI is a sum standard, but every form can use this standard or formal description to create some implementation of MPI implementation. So here, production form. So in some implementations, some functions they obey the standard, but can do something else. In this case, send MPI send is not blocking operation. Somehow, this is just due to implementation of this MPI library. But receive, if we change the order, and firstly will be receive, we can see a deadlock. That means no. That means receive is a blocking operation. So you can use these specific things, or you cannot. I mean that MPI send is not blocking operation. But maybe using your code, if you do not keep in mind that MPI send is blocking, and you think that it is unblocking, non-blocking operation, you just take your code and run it on another cluster, and implementation of MPI on this cluster, another one. And in this implementation, this MPI send function, for example, is blocking operation, and your code will not work. So
if they can make MPI send non-block in one cluster, why not just make it globally non-block?
Because there are some non-blocking operation in the standard of MPI, and we will consider these operations just a couple of minutes. So what I want to say is that nonetheless, MPI send, for example, blocking or non-blocking, you should or even must think that it is blocking operation and do the same way.
But let's say time-wise, if I have two MPI sends, but yet it's a blocking operation.
Yes, you think so. You should think so.
But will it take, in retrospect, more time than you could have received, send, receive? Will it take more time to have two sends in the same process?
If you use once more, please, on one process will be.
No, so suppose we have the deadlock thing where we have two sent in one process and then the second one is received. This is going to be a deadlock. Does the receive work? We should think it doesn't work, but it works.
Yes.
But what if we have, and will this case be the same amount of time as if we have on this first process send, receive, and in the second one receive and send? Will it be the same time?
I think it will work a little bit faster. The second one. I think, but from other side, I think that we do not have to take into account this difference, because I think maybe a little, maybe will be almost the same. Just do not.
Negligible amount of difference.
Yes, maybe, but I think we do not need to take into account. So another way to avoid this deadlock is using non-blocking operation as it is MPI I-send and MPI I-receive, and some additional function MPI wait. So let's see. When it was deadlock was then firstly we use MPI receive here and MPI receive here. So let's see once more. We can see deadlock. Our program is frozen. Okay. Stop. And now instead of using MPI receive blocking operation, I want to use MPI I receive, which is a non-blocking operation. Here and okay here. So what is it? It is the arguments are almost the same. So address, amount, the type, to the process, number of process to whom, tag, communicator, and some operation or some variable request. It has MPI request type, just new additional variable with this type. When you use this non-blocking function, a process just initiate the receiving or sending. This information will be in some buffer, and process will continue its operations. It will work further. It will not stop. Okay, we'll see. Just we'll see and break. It's okay now. So if I use non-blocking operation MPI I receive instead of MPI receive, my program will not frozen.
But sir, what makes I receive and receive a non-blocking and blocking operations? What makes them different?
So when you use blocking operation, process will stop until on the other side the message will be sent to it. We'll wait. If there will be no any sending function on the other side, that means it will frozen forever. Deadlock. But when you use I receive, for example, so non-blocking operation, it's just initiate this operation, and it will be completed when on the other side the sending message will be.
But if there's no sending message,
on the background, in the background. So this process will be somehow in background, but process itself will continue working. And in this case, deadlock will never happen. So a little break. So it seems that using a receive function in this like this can solve this issue of deadlock, but there is another issue. What is this? What I mean? For example, here process 0, for example, and try to send. So use a non-blocking operation. So in the background, maybe there is some sending process, and process number 1 receive this. Suppose this was a large amount of data, some big array, and maybe even it bigger than some buffer. So if process number 0, it will continue its working. Try to change this array. What will happen in this case? While the sending is
error. It's going to be a problem.
Why?
It's in the process of sending. Then you have to intercept the send, and you have to change it, and then send again.
No, maybe send again, not send again. Other opinions. What will happen? What do you think? This is array.
It's going to send a new values. Because when it's in the process of sending, for example, since it's still sending the buffer, so if you change the element of the buffer, that's what's going to be sent during the process, which is not what the person wanted to send in the beginning.
Okay, yeah, you're right. These are elements of the array. And suppose that sending will start from here, and every other element will be sending. Yes? So array is rather big, and I send will change some element here. For example, it was 0 and it changed to 1. And process of sending start to send not the 0 but 1.
But what if it's already
and this will be another array, not the array of beginning sending, of initial sending, not this array, but another array with new data, and maybe on the other side it will course the illegal result or non-correct answer. So what should we do in this case? Yes, compare weight. So here, before changing the sending data, we should wait until this sending will end. So here should be some wait operation.
But if we're going to use wait, why not just use send instead of isend?
Because here you can spend this time. So do something useful. So process between isend and wait can do something useful operations, and not just wait till this big array will send and receive and so on. And maybe it will never change this array. In this case, or in the case where this sending is already ended, finished, there will be no waiting in this place, in this line. So if process encounter with wait and the sending operation already finished, that means it will go through this wait function and continue, for example, change array and so on. It can do this because the sending is already finished, and it will be okay.
But sir, let's say in the example that you gave, if it's 0, it comes to be 1, right? What if like you want to change like the first element and the first element was already sent? What's going to happen then?
Maybe the sending will be okay, maybe, but who knows? You will never know. Nobody.
Yes.
That's why there is some additional function MPI_wait, and this MPI_wait has as an argument the request variable that was in the MPI_receive or I_request function. So this is almost the same as it was in this code. But what do you say about the correctness of this code here? How do you think?
I think maybe the MPI wait should be between the MPI's I send and MPI I receive.
It's a worm, almost right. And if in your case should be MPI_wait after I receive like this, so you say it should be between, but after I receive, should be.
No, so if the wait is going to be after the I receive, it's just going to be a receive function. Therefore, what's the point of using I receive if we're going to use the wait after? Therefore, I think maybe we should use the wait after the I send.
Yes, you're right. So you can see that if we use in such way, we can check just the last operation with this request. You can see here and here, but this information will be lost about this operation, and we, in this case, we cannot check. Will it was it finished or not? So yes, you're right. Some MPI_wait operations should be between and maybe not in between, but before this array will change, before this line, and maybe these two operations should be here, MPI_wait and MPI_wait. It's okay if you change your array after these two wait operations, maybe here. But in this case also you have to use different names of these variables. For example, request1 and request2, and check these two requests 1 and 2. And maybe if there are a lot of operations, you can use even array of requests. Okay?
So what exactly is the blocking operation and what's the definition?
What is the definition of what?
Definition of a blocking operation.
What does it mean, definition of blocking? We have discussed this on the first seminar.
Okay, I think I forgot.
Okay, almost the same. Definition of blocking, what do you mean? Arguments,
okay, if some function, MPI function, how do I know if it's blocking or not?
Okay.
Let's assume it's not a function we discussed in class. I just see one. How do I know if it's blocking or not?
Okay, because of its name, it is called as MPI I send, I receive, and blocking operation will be like just MPI send, and just MPI receive. Here you can see.
Yeah, but these are functions we've discussed in class. What if I see a function we've not discussed in class? How will I know if it's blocking or not?
So the blocking operation is just without I before send, for example. Or just if you see send, it is there are another some, for example, with buffer and send, and we will not discuss because they are used very rare, but they also can be blocking and non-blocking. And if you see I before receive and I before send, for example, okay, it can block in B, send, B. Okay, in our cases, okay, let it be. If you see I before receive, that means non-blocking.
Blocking means no I.
Yes, and blocking without I. But, by the way, you have to, if you will see something that's not usual for you, you just open book and you can see, yes, it's, and read some documentation. About wait, okay. We can use wait here, for example, it doesn't matter. And about the third way to solve deadlock issue is just using MPI send receive function, which includes the sending and receiving operations in just one function. It has a lot of arguments, but all these arguments are almost the same as it was in send function and receive function. They just combined. So you can see first 5 arguments is for sending, 5 further arguments is for receiving, and other 2 is just the name of communicator and variable status. That's all.
So why don't we just always use send receive instead of using send and receive or using isend if it works so good?
Yes, you're right. The question is has some point of consideration. By the way, in reality, almost all people use non-blocking operations because they are more efficient. But in our classes, we will use just blocking operation because some interesting situations if you use just non-blocking operations, all will be okay. If you use wait operations, and your code will work fast. Using blocking operation, there are different ways, and the behavior of working of your program will be depend on how you arrange the sending and receiving operations. Will be depend on the algorithm of exchanging data, and it is interesting, and we will discuss today this because of the way you arrange the sending and receiving, your program will work or will work in different ways, and it is interesting. But if you use iReceive, these specific things will be lost. Always your program with non-blocking operation will show good efficiency.
So suppose we're not doing like work in class or homework. Suppose we're actually applying MPIs in the workplace. We'll basically mostly 99% of the time use non-blocking MPI calls. So I understand.
So, but if you will understand how to use blocking operation, you always will be so it will be easy for you to use instead of blocking, non-blocking, and all will be okay. But you will lose some interesting things.
Yes, sir. And so in send receive it's a blocking operation as well.
Send receive, yes, it's blocking operation, and it's up to you to use it or not to use it because of conveniently. Some people love to use it, like to use this operation. I, for example, do not like to use this because for me it's not transparent somehow. Other people like because they okay, just one operation and there is no any deadlock, for example, and so on. I like to use it. Okay, it's more convenient for you, for me, for example, to use it and so on. So it's up to you to use or not to use.
And is there also MPI send receive?
No, it's just one blocking operation. And so one also specific thing.
So does MPI send receive cause deadlock?
No, it's your or it's okay. How to say? So it is was created to avoid deadlock. Even it is a blocking operation. That means if one process tries to send something, and other process will not achieve this function, so that means it has not start to receive. That means the first process will wait. You understand? But block will never happen. These two different things, block and waitings.
So block, everything below it never happen.
Yes.
Wait is just wait until we get an answer and then we'll continue.
Yes.
So this send receive uses wait, not block.
Yes. So
What?
no. It's blocking operation, and some process will wait the answer of another if they are on different time levels, but it will never block.
So my question is, how, let's say, in wait, how long does it wait? Let's say it doesn't receive an answer from the second process.
So in this way also, okay, it will block. It will be blocked if on the other side there is no this. So if on the other side there is no any answer from another process, okay, it will block, or it will block, and it will wait forever. But this is somehow not the classical deadlock. Just waiting, the forever waiting of another process.
So what time, like, let's say, what time should I use blocking MPI call, or where should I use a non-blocking but with a wait? It basically does the same thing. There's no real difference between.
No. If there is a blocking operation and process, okay, let's see. So the differences between here blocking and non-blocking operations, yes? So process number 0, number 1, and here S sending. Oh no, let it be faster. Faster, I mean this arrow will have more length. So here S sending, blocking sending. Here you can see process number 1, which works more slowly, and there is some delta t till this process achieve this point. Here will be receive, and here will be some delta t sending. So all the time delta t will be delta t of waiting plus delta t sending, yes? And after that, here will be also delta TS, here the same level, and after this sentence will finish, they will start almost simultaneously from this point. Okay? Non-blocking. Here will be process number 0, 1. The same will be faster, and I send. Okay, let it be capital I, yes, like this. And process number 1 is slow, but consider this point. If in this case this process was blocked, we'll wait until this process number 1 achieve this point. But now process number 0 continues working.
So it's only going to take PW.
So this was delta t, but delta t, okay, 1, okay, and will be the same as delta t1. And if process number 0 wants to change this variable a here, a equals to b, for example, and before this we see wait, and sending has finished before, and process also works here. So this process will never wait something. Here we can see delta t equals to some value, and here we can see delta t equals almost 0.
Wow.
Maybe in some case, if you want to change, if process 0, okay, let it be new page. Maybe if you then, I mean, if process number 0 wants to change variable a here, for example, that means wait will be here. That means time of working, let it be delta 2, and after that it will wait until the sending will be finished, and it will wait this time delta t1 minus delta t2 and plus time of sendings delta ts, and all waiting time will be delta t1 minus delta t2 plus delta ts. So in this case, this delta t will not be 0, but it will be less than delta t waiting plus delta t sending when there is blocking operations. Blocking. Non-blocking. So this depends on where process number 0 want to change the variable that was sent. That was sent.
So can you go back to the last slide? I want to finish talking.
So when using non-blocking operations, the waiting time can be 0, but in bad situations, it will be greater than 0, but will be less than this waiting time when you use blocking operation. Because it depends on where this process wants to change the variable.
You said in our course you want us to use blocking operations.
Yes.
Therefore, as I understood, blocking operation is going to be equal to the sum.
Huh?
So you said the blocking operation is going to be delta sum, delta t equals delta t value plus delta ts. So we have to think about the sum in terms of time.
No, maybe yes. This is just some explaining of differences between blocking and blocking. Maybe in your operations delta t, okay, delta ts will be comparable maybe with delta t wait. Yes, maybe. Okay, but the real values I don't know. How many seconds or milliseconds every process will wait and will send. Okay. So, have you any questions about the deadlock and how to avoid this situation? Okay, but 1 minute. MPI receive, send receive. You can use this function not to exchange data with just one process, but you can see that you can send to one process and receive from another process, and even receive different types of data. Okay. You can send to left and to receive from right somehow. And on the other side, processes can use different functions. I mean, receive, I receive, or even send, receive, and so on. It doesn't matter. But one thing: these arrays, when sending and receiving arrays, should be different. Because, for example, let's suppose a situation when you send and receive just one array. That means you receive something, and at the same time you write into this variable something. And okay, this is some strange, and you can send worse data. Okay. We'll comment these lines. Okay, any source. Let it be any. Consider any source. So what is it? What it is? You can see that in every send and receive operation, you can see to whom this information, or from, so the number of processes, and you can see the tag. It's some tag or some number of message and so on. But you can use, instead of these numbers, some identifiers or constants, MPI any source and MPI any tag, predefined constants. So MPI any source, that means you can receive some information, it doesn't matter from whom. For example, every process we have considered loop, and in this loop, process number 0 receive every information from other processes. Yes, like this. For I from 1 to I size -1, I++, and process number 0, and it receives some information from process I. No, let's suppose from tag I. What does it mean? Consider other processes. For example, 1, 2, 3. Let it be 3 other processes. You can see that process number 2 is fast one, 3 a little bit slower, and the first one is very slow. What will be in this case when you use I and blocking operation? That means process number 0 will wait and here the level of sending. Process number 2 achieve this point firstly and will wait, because this is blocking operation. Will wait until which time?
Until process 1 has sent its own and process 0 has received from process 1.
Yes, and on the side, and maybe on the and process number 0. Let's suppose process number 0 even faster here, and this is first receive operation, and it wants from wait from 1. So process number 2 will wait, process number 0 will wait this time, and even process number 3 will wait. So what is the situation? Process number 2 achieve this point and wait. After that, process number 3 achieve this point and will wait. Wait. After that, process number 1 achieve this point, and there is an exchange between 0 and 1. After that, I will be 2, and process number 0 will receive from 2. After that, I will be 3, and process number 0 will receive from 3, and so on. But all 3 processes will wait to process number 1, the very slow process. Yes? What will be if we will use, instead of I, here any source? Any source. What will be?
No, wait.
What is not the any source?
So that means
It can receive from 1 or 2 or 3 anyway.
yes, you're right. If there is any source here, that means when to achieve this point, process number 0 can receive information from 2, because it doesn't matter what is the number of process from which this information will be. And process number 2 will send something and continue to work. And
so if we use any source, do we use while loop now?
It doesn't matter, I suppose. But while loop, I mean, what is the counter in this while loop? What? The number of the whole number of processes.
Okay, so if we use for loop,
it doesn't matter. You have you just should describe the whole number of processes which should exchange or some information. For example, here this counter should be 1, 2, 3, whole 3 processes. You can use while loop, but it should run 2 or 3 iterations. The iterations should be equal to number of processes and so on. After that, process number 0 will wait a little bit before process number 3 achieve this point and send, and process number 0 will receive this. If in the first case, and so on. After that, process number 3 will continue, and process number 0 will wait until process number 1 achieve this point. In the first situation, the order of receiving will be just the order of this loop, order of this loop counter. 1, 2, 3, with a lot of waiting time. Especially on the other side, first situation. If you use any source, the order will be different. 2, 3, 1.
So that means any source.
Any source. Any tag, almost the same, but for example, it doesn't matter what is the tag. One process will change, for example, 1000. Will send 1000, for example, messages to another process, and it doesn't matter with somehow, and it doesn't matter which tag will be first or last. For example, there is some if statement, if some situation that if will be like this and the tag will be like this, if will go on another branch, tag will be different. But for two processes which receive information, it doesn't matter which is the branch on the other side. It wants just to receive something, and you can use just any tag, receive. It doesn't matter from which branch will be, and so on.
Can it be a case where we use the same process more than once if we use any source? Let's say if we use process 2, and because on the second time we choose the process 2 again, can it happen?
I think yes, why not? You have consider that the receive operations should be equal, the number of these receive operations should be equal to send operations. If it will be greater, it will be somehow deadlock or forever waiting. So the number of these operations should be the same, and it doesn't matter the number of process, number of tags. You should consider just the amount should be equal to each other, and so on. So this is about any tag. Okay, consider this, I suppose, after break. Okay, let's continue. Let's see what will be if use any tag or any source, I mean, or not to use any source. Here you can see some code. You can see the same loop as it was in my explanation. You can see here I, and this is the same way, like this. So we suppose that if print some information after receiving, we'll see the order in which process number 0 will receive information. Other processes just send some b, some value, and so on, some variable. What this? And let it be, 4 processes. You can see the order 1, 2, 3. 1, 2, 3, 1, 2, 3. So every time the same order of appearance. Okay? Okay, change to any source. One, two, three. 1, 3, 1, 3, 2. The order has changed. 2, 1, 3. The order of appearance. 2, 3, 1. Every time I launch my program, the order of appearance will be different. So, this way, this situation. Okay? And continue, and about status variable. This status variable is, by the way, the structure with 3 fields, from which tag and some error, if there it was. MPI status, MPI source, from which process this message has been received. Status MPI tag, so the same tag of this message, and error if some error has encountered, and so on. Here, for example, if I use MPI any source, this process doesn't know about the number of processes from which this message was received. Yes? So in this case, I just use status MPI source. So this information will be here, and I can print this information using field MPI source. And you can see that this field is okay. 2, 3, 1, this MPI source.
When does status change? So, in what part of the code does status change?
I didn't catch. Status change here. Every time process number 0 receive, status will be another.
Okay. And we can make status 1 status, 2 status.
Of course, of course. So, any tag will be almost the same. Let's see. Any tag. It's simple. So any tag, the same loop, for example, and if there is one process number 0 will wait 2 messages from every process. So if there is process with tag, if there is process with number more than 0, you can see it will send something with tag from one order of tags and another of tags, which the order will depend on this variable, for example. Okay, somehow. And we'll see. You can see that firstly, that it's a little complex, but we can decipherate these lines. Okay, so you can see every time every process will send B equals to rank, and if A equals to 3, the order of text will be 3 and then 2. Firstly, you can see that the message was from rank 3, this text 3. It's okay. The order of text should be 3, 2 in just one process. Okay, we can see the same. The same will be with process number 2, the order of text the same, and for process number 1, order of the text will be the same. Okay, if we change this order, so now should be 2 and then 3 text, I mean. You can see there is no any deadlock and so on. All process number 0 receives all messages, and you can see the tag, this order of text has different order because process number 0 receive with any tag. And you can see that to print the MPI source and tag, I use MPI mini source, any tag, and MPI error. But error, you can see, always 0. So if there is no any error, the code of this error will be 0. If there is some error, I don't know which one, because I have never encountered with such a situation, by the way. So error will be the code of this error, and if you encounter this with this error, you can show this code or can use this code to read something in documentation and so on. But I think that you will never do this because I have never encountered with some such situation. So, have you any questions about any source, any tag? Okay. Here you can see the some value for non-existent process if you want if you want processes to send something to its neighbor if rank of process larger on Unity and less than on Unity in comparison with the number of current process. You can say that neighbor from the left neighbor and from the right neighbor. If you want processes to send something to its right neighbor, that means every process will send information to process with rank greater on Unity. But you can, if process with the number of size -1 send something to the process which greater, what will be? What is the maximum number of processes? Size -1. And what will be if size -1 will send something to non-existent process?
It's going to be error.
Yes, it will be error. So if there is if you want to do this in a logical way, so every operation should be in every process in the same way, I mean, or you want to, okay, it's logically very convenient when you do something and every process do the same. And you just write the same thing in every process, and every process does these things. But if you can't do this for the last process, for example, because it tries to send something to non-existent process, you can just use some a special value for this non-existent process. For example, MPI process null. This process does not exist. And by the way, in fact, the reception or sending will not occur. Will not occur, but there will be no any error in this way. So it's for conveniency, for example. Okay. Another interesting thing. When you do you remember when, for example, 0 some loop and 0 sends something, the part of array, for example, some array, and for example 10 elements, it doesn't matter. And if ranks non-zero, they receive, yes? But how many elements should other processes receive? Do they know about this? How many elements? No. They do not know about this.
How many elements of what?
Of array. So.
Or the size of the array?
Not 0. Process number 0 tries to send part of this array, and this part equals the size of this part equals to 10 elements, or 11, or like n over size plus 1 or not plus 1, like it was in first program. How many elements? I don't know. I do not know, and every process also does not know about the amount of elements which it will receive. So in this way, you use just another send function, yes? Send some value, some variable, and this variable contains the amount of element which every process should receive in next receiving, yes, in next message. And firstly, every process should receive in some buffer variable the amount and use here this amount. In this case, you can see this is additional message, additional exchanging operation, which takes some time. If there will be a lot of such an exchange, so every time you add some message, and it will take some time. And if there are a lot of such an operations, this time will be also a lot, will be much. So to avoid this time-consuming operation, time-consuming sendings, we can use some functionality of MPI. Additional functions, MPI probe and MPI get count. They are used together. So MPI probe, here this is the number of processes from which this message tag, the name of a communicator and status. Okay, and MPI get count. In variable count will be written the number of elements the number of elements of which has type integer, for example, and we will some look through this message using status and somehow look through it like X-ray. And knowing its type, we see, okay, MPI see the amount in bytes. If you know the type of variable, you can divide the amount of bytes on this amount of one type and calculates the number of elements. All this work does just MPI, and the amount of elements will be in the variable count variable, and after that you can use count in next receiving operation. And every process just once send, and the receiving process is just once receive. Okay, we'll see like this. So you can see process number 0 in a loop fulfill the array, and you can see it sends 5 elements from every beginning to process number 1. Yes, 5 elements. And the second element, not the 1, but 10. Okay, it doesn't matter. And process number 1 use probe. This is the number of process from which this message tag, and get count. Here you can see count is an integer variable. This is its declaration, and after that we can print and use this variable to receive 5 elements and write these 5 elements from the very beginning of array and print the array and so on. Okay.
Does the probe put anything in the status variable?
Of course, yes. In the status will be from which tag, error, and get count in this way. It knows about message because it knows what is the message under consideration, because it knows number, tag, and so on. So you can see, firstly, rank 1 should print count. Count, you can see, equals to 5. Daniel, can you see? Okay. So 5 elements here, and probe, using probe and get count, you can see that count equals to 5 here.
Yes, sir.
After that, process number 1 prints all elements of array. But we know that first 5 elements were from process number 0, and it should be 1 or 0, 100, 2, 3, 4. 0, 100, 2, 3, 4, and after that 5 further elements contain some garbage. Okay, this is how probe and get counts together work. It is a rather useful thing. Yes? Not. So, any questions?
No, sir.
Go further.
Yes, sir.
Okay, now we will talk about collective operations. We have discussed this MPI barrel before. I think already you have know already about this, yes? But maybe it will be interesting to repeat once more about barrier. So here about time, measurement of time. Every process, first and the main thing is that every call of collective operation must be in every process, because this is collective operation, and in this operation every process takes part as a whole. All processes should be. Okay, and here you can see that, for example, here 10 million elements, and every process summarizes these elements, and it will be 1 million in every process. And process number 0 after that receive this with any source. So this is situation that without barrier, the finish time will be much different between every processes, because somehow some process will be faster, some will be slower, and if we use any source as it was before, the finish time will be much less between every process. So we'll see what will be if we use MPI barrier, what is the difference, and if we will not use this barrier. Okay, so with barrier we'll see this situation when every process consume much time, and because of we are on the client machine, these times will differ from each other, and the end in the finish time will be also different. So we'll see. The operation of saving is very slow somehow. Okay. Sum is okay. 20 millions. Finish 1 or 2. Okay, let it be 5 processes, for example. 5, 4. So you can see the difference. 3 last digits is approximately more than 100. Yes, the difference. Here you can see 500 and see more than 6. The difference will be more than 100. Yes. Here difference is not so much. Here, you can see the difference between these two prints is more than 200. What will be if there is no any barrier? This is the difference. Not 2 or 100 the last digits, but more than 1,000 the difference. Here you can see even 1,050 hundredths. This is without barrier. And after barrier, why is it so? Because here all these 3 processes will be fast, and this process somehow works slower. But if there is a barrier, that means after barrier they start almost simultaneously, and these times differ not so much. But here you can see, without barrier, the difference is much larger. Also the same thing, more than 1,000.
But between process 1 and 2, 1 and 2 is not that much.
Not that much. It's somehow stochastic process. I don't know how to explain this behavior. So, yes, every time. I know. I know this. How to explain? Suppose. Because I know. Because we use any source, that means every process. Rank 0 will be the last process that will print this line, because it will wait all the processes. It doesn't matter the order, but if, for example, process number 2 firstly finish its work, that means it will be the first process which sends the information, sends message, and here it sends and goes here and print. Will be the very fast. Process number 0 firstly receive from process number 2, and the next step will be receiving from, for example, process number 1. Let it be. Okay, process number 1 sends secondly after process number 2, goes here and print information. Process number 0 receive from process number 1, goes next step, and receive some information from process next one, 3, this one. So process number 0, the time of process number 0 will be, the biggest one. So you can see here, yes, it will be the biggest one, I suppose. Yes. But when, here you can see biggest one. But if we turn on the barrier, include barrier, you can see the times
They're more stable.
More stable. How? Why is it so? No more stable. Oh, here. So the barrier is, as it was discussed before, some point where all processes wait each other, and after that they start almost simultaneously. Okay. Let's go further, I suppose, because it's a little bit slower. And broadcasting. The broadcasting is a collective operation where the information, some information, spreads or broadcasts to from one process to other processes. So process number 0 fulfills the array, and after that, okay, like this. Here are the arguments. So from 0, 10 elements of array will be spread or broadcast to other processes and this process itself. That's all. In our case, it will be from process number 0, 5 elements from the very beginning of array. And we'll see what will be after broadcasting. So in process number 0, after broadcasting, it will be the same array and the same elements. But we'll see what will be in other processes before broadcasting. Broadcast, because this is a collective operation, and it should be presented in all processes because it is collective. And what will be after broadcasting? Okay? We'll see. Let it be a little bit less. So, process number 1, before broadcasting, there is a garbage in every element. Process number 0 after broadcasting is the same array, and after broadcasting in process number 1, the process number 0 broadcasts just first 5 elements. And you can see this is the same elements. 5 elements after broadcasting. 5 elements is okay, but other 5 elements is garbage.
What happens if we do 4 processes?
We'll see. 4 processes, yes.
So most of them keep the 5 elements.
5 elements in every process after broadcasts will be the same. And before, you can see garbage in every process, not here, before here, here, here. So this is garbage. Like this. Some variable a from 0 will be broadcast to other processes 1, 2, 3, 4, 5 numbers, and this information will be also written in the same variable a. Okay.
Can we go back to the code?
Huh?
Can we go back to the code? So this MBIP casts, why do we need it in the other ranks if they are not the ones broadcasting? Well, what does the line on 185 do?
185, this one. These lines, so it shows every process that the broadcasting is from process number 0, firstly. So process number 0 here, it has the array of 10 elements, and this array is fulfilled. Yes? After that, so if this line is in every process, that means every process sees this line, and every process knows that broadcasting from 0 and the 5 elements of array from 0 will be written in the same array, I mean the array with the same name in every process, and will be written every first 5 elements with type int. Okay? But because this is a collective operation, it should be in every process. It should be presented in every process. Have you answered your question? Or no?
My question is, that line, does it say that this rank receives from process 0, because
which rank? This
rank not equals to 0, yes.
Yes, no, somehow yes, of course.
It tells the rank.
And every process number 0 also you can think in such a way that process number 0 from 0 writes 5 elements into the same array. So the same.
So I'm just wondering how one function can send and receive as. So
because
it's sending or receiving.
This is the functionality of collective operations, and somehow inside this B cost, you can imagine that sending will be from 0 and receiving will be in other processes.
Okay. I understand the purpose. I'm just wondering how one function can do that. Because if this line 166 is sending to the other ranks this first 5 elements of the array, how come the other ranks are also not sending? They are only receiving.
Because this 0 is the number of process from which is sent. Yes,
okay.
Which sends. This is number of this. If the rank equals to 1, okay, it knows I'm 1, not 0. That means I will receive. Okay. Okay, break. 5 minutes break. Okay, scatter. So this is okay. You can see a lot of arguments, but the main thing is the process number 0 sends 10 elements of this array from firstly sending, type integer, to buffer which is located in other processes, and it is written there are not okay, it is written 10 elements, and this array is divided on equal parts. So every next 10 elements, every next part of 10 elements will be sent into the next process. So this is the same situation as it was when you okay, let's open this one here. When it was in first program, in first task in your problem, when you tried to send every other part of your array into the next process, okay? And the size of this part equals to n over size, and you move the address of the beginning of each part. Yes? This is the same. Let's see. If we are in process number 0, so this is a fulfillment of this array, and print, okay. It's another. It was doesn't need. Now this was to check something, but now it is not necessary. Okay. So array is fulfilled, but there is another array which is called some buffer. Okay, before scatter process, just print this buffer, and we suppose that inside this buffer will be garbage. Okay, scatter. So in scatter, first 3 elements will be sent to first elements in the buffer. And we'll see what will be in the buffer after scatter process. Okay? And other ranks also buffer before scatter, scatter, and buffer after scatter. Okay? Let's see. Strange behavior. Let's start with small amount of processes. So, process number 0, okay, array, the main array from which first 3 elements will be sent to other processes and process number 0 itself. So before scatter process number 1 show us that there is a garbage. After scatter process you can see, after scatter process you can see that in the buffer first 3 elements equals to first 3 elements of array. Yes? In process number 1, number 1 here, after scatter, you can see that its first 3 elements is the next part of 3 elements from process number 0. Okay? Do you see? But somehow it's I think this is not necessary here. Confusing.
Can I see where the buffer is written, where it's declared in the code?
Here, in process number 0, and here in process.
But like, when did we initialize it? When did we declare the variable?
Declare a buff in the very beginning of my code here.
Okay.
Let's see. For example, using 4 processes. So, why is it so? Where is the array itself? Okay, not here. Okay, it should be here. Something. Okay, let it be like this. It works, so it's okay. Okay. Here we can see array itself, which will be divided into parts, and every part will be sending into other processes. Okay, we'll see. So before scatter in process number 0, garbage. After scatter in process number 1, first 3 elements. Okay. Further, before scatter in process number 1, garbage. After scatter, second part of 3 elements. Process number 2, before garbage, after the next next 3 elements here. Yes? And in process number 4, just 1 element, 9. Because there are 4 processes and 10 elements, and 10 over 4 will give you a remainder. Yes? you can see that, okay, you can see that all the array will be divided into parts, and every part will be in every process. But you can see that the amount of elements in every process will differ more than one. When you divide by yourself, you can make this as you want. You can do like this, or you can spread the remainder more uniformly. Okay, here you can see that this will work, but of course it will work more correct or more precise. I mean, if there is no any remainder when array, the number of elements in array will be divided by the number of processes. It will be more efficient, something like this. But you can see that it will work and it's okay. Have you questions? Okay, go further. MPI gather is the scatter vice versa. It will collect information from other processes the same way. From process number 0, collects 10 elements from every array, from every process, and construct new big buffer. Okay, it should be declared before, and it should be big, and it will construct this buffer from the bricks from other processes. Bricks of here, every brick contains 10 elements. From one brick of 10 elements, after that another brick of 10 elements, and so on and so on. And every brick from the process with much larger number rank.
Sir,
Yes.
for the scatter,
Yes.
if let's assume we put 4 and 3 instead, what will happen?
What will happen in which way?
For example, in line 214, if you say array, comma 4, buffer, comma 3.
Okay, let's see. We can answer this question easily. So 4 and buffer 3, we should change the same in every process. So should be okay. These lines will be different. It should be the same, but let it be different. We'll see what will happen. Okay. You can see an error. An error occurred in MPI scatter. Okay, because these lines, this one and this one are different, not the same. Okay, let they be the same.
Still error again.
Yes? Okay, you can see an error occurred in MPI scatter because this and this are not the same. Because you divide, okay, process number 0 tries to divide its array into parts of 4 elements. And how MPI should know, I don't know, to construct, okay, to write some information. There will be a lost information, by the way. So one element will be lost in every brick. Okay, so you can see we can change vice versa, and we'll see. And you can see and you can answer your question by yourself if you use, for example, your code. Or I can give you this code and you can play with it at home. Of course, I will give you. So you can see that there are no any errors, but you should we have to know. Okay, we should see what will happen in this case. So every 3, but we will write 4. You can see before scatter 3. This is, I suppose this is a garbage. Process number 2 before scatter. Okay, before scatter garbage. After 6, 7, 8. 6, 7, and where is process number 1? Here we can see before garbage, after 3, 4, 8. 3, 4, 8. No, it's okay. Okay, you can see that if we write more, here tries to run more, it's okay. If we tries to write less, it's this scenario. You can play it by yourself. What will be? Okay, comment and go further. Okay, I have said about gather, yes, and we need to see what will happen. So here, process number 0 fulfills the array as its rank. So every element in this array will be 0. And in every process array, all the elements of the array will be equal to the rank of this process. After that, before process, we can see that buffer should contain garbage. And process number 0 somehow will send 3 elements from the array, and these 3 elements as a one brick will be put it in the very beginning of buffer. Okay, and we'll see what will be. After that, here every process also knows about what? About 0 will construct buffer. Every brick will contain 3 elements, and process number 1 will 3 elements, and these elements will be equal to its rank unity 1, 3 ones, and this brick will be after 0, 0, 0. The brick from process number 2, 3, 2, 2, 2, will be after 1, 1, 1. Okay, we'll see. This is our consideration. What will be? Yes, we'll see.
But it might be random. Maybe 2, 2, 2 might come from 1, 1, 1, right?
No. Okay. Small amount of processes. Here, before. Wait, what is this? This is broadcasting. Because here, I imagine why this line is always here. So you can see. What we can see before, where is before? once more. Why we cannot see this line before gather process? I don't know. Why we cannot see?
Process 0?
For example, yes, before gather process, this line, we can't. I can't see here. Yes. Before before yes, after yes, and what about process number 1 does not print any information. Okay, it's okay. So you can see before gather process, it's a garbage inside the buffer. But after gather process, you can see 3 elements from 0 and 3 elements from process number 1, and after that there is a garbage. Okay. What will be if we will use 4 elements? 4 elements. Oh, 4 processes. So 3 elements from process number 0, 3 elements from process number 1, 3 elements from process number 2, and this array contains only 10 elements. But we can see that 3 times 3 will be 9, and there is just one free place. Yes, and we can see that process number 0 in the last bricks cannot contain all 3 elements. Yes, because we just have one place. This will be just 1, 3.
My question is why isn't it random?
Why
isn't it random, the order of the...
Because this is how this function works. Is there?
It goes from process 0 to process 1.
Yes. This is how to say. It's the declaration of its working. That every block from the process with the number larger will be after, and so on.
But what about something like MPI, any source? What if some process takes so long?
Here you cannot see any source because this is a collective operations, and all processes are in the process of exchanging information. So you can see just one process that in the case of scatter divide the array inside it, or construct some array, just one process. Okay? Okay. Any questions? No? Okay, and the last slide, the last useful collective operation is MPI reduce. So this is all operations almost the same. So here process number 0 collects in the buffer some result of operation, which this operation on the elements of array which are in all processes. Okay, and this operation, for example, will be sum or product or some logical operation like AND, OR, NAND, NOT, and so on. Okay, consider one operation, for example, sum. For example, here 0, 1, 2. This is array, and here array, and here, and here. Array. Okay, consider ith element. If there is a plus operation, it should be here, and in the buff, here above, I, and we can say like this, I in buff in process number 0 will be sum j from 0 to size -1 I from array from every process, something like this. So the result of this summarize will be in process number 0, and it will be in some array which is called buff. In this operation will be on every element here, in every element of array, and the result will be in every element of buff. Do you understand? Okay, we'll see on the code. So what we see, rank 0 fulfills the array. Before reduce, it prints buffer, so result array. Reduce, so in process number 0, in buff, it will construct some buff, and it will construct just first 7 elements, and every element, every 7, okay, consider first 7 elements in array in each process, and all these elements from other processes will be collect, summarize, and will be put it into the buffer which is in the process number 0, and we will see the result. We'll see the result what will be in other processes. Okay, they also fulfill the same collective operation, and we'll see what will be in the buffer in other processes. Will it change or not?
No, it will not change.
Yes, you're right. Okay, we'll see.
So buffer of I is equal to I times size minus 1.
Okay, like this. Start with a small amount of processes. So you can see array in each process like this. So if there is just 2 processes, that means in the result buffer will be 0, 2, 4, 6, 8, 10. So every element will be multiplied by 2, yes, because 2 processes. And you can see that after reduce in process number 0, we can see the result, and you can see that this result will be inside first 7 elements, because we deal with just these 2 first 7 elements. And you can see that before reduce in process number 0 there is a garbage, And after reducing process number 1, there is also a garbage. So the result will be just in process number 0. Okay. What will be if we consider 4 processes? That means every element will be multiplied by 4. Okay? And you can see the result. 1 times 4, 4, 2 times 4, 8, 4 times 4, 16, and so on. And this is the 7th element, and 6 times 4 will be 24. And further 3 elements, it's a garbage. And you can see that after reduce in process 2, 1, and 3, there's a garbage. So the result, okay, we can see that all the result is in just process number 0. Okay. So, and the last one is all reduce. All reduce when the result will be in all processes, not just in the process number 0, but in all processes. Let's see.
So now after reduce, it's going to be in all of them.
That means all processes know about this operation, and answer will be inside all processes. So you can see before reduce garbage, after reduce no. Why is it so? 1 minute. I see. This is product. Product means multiplier, not summarizing, but we can just the example of another operation. So if the product means 1 times 1 times 1 times 1 will be 1, 2 will be in power of 4 will be 16. 3 in power of 4 will be 81. Okay, it's okay. 4 in power will be 16, 64, and times 4 will be 256, and so on. But you can see that this result will be in every process. After reduce, process 1, 0, 2, 3, you can see that this is the answer will be in every process. Okay, have you any questions about collective operations? So we have discussed about, let's remind, okay, first deadlock. And deadlock, you can avoid deadlock using 3 ways. Change order of operations, using non-blocking operations, and using send-receive operation. Okay, this is about deadlock. So any source, any tag, it can be convenient, and it can save time when you deal with a lot of processes, and especially when some process collect information from other processes and so on. If you use any source or any tag, by the way, this process or some process that receives some information doesn't know about the number, but it can to know through status. The same source, tag, and error. Error, I suppose, will be always equals to 0. Nice, and some special value, some constant for non-existent process. Okay. To know how many elements will be received without additional sending, You can use probe and combination of probe and get count functions, and without any additional time-consuming operation. Okay. And about collective functions. Firstly, every call of collective operation should be presented in every process because it is collective. Other way, it will be an error. And we can see that the form or this line should be equal, should be the same. If there is some difference between calls in some point, in some value, will be an error. So barrier is a barrier after. By the way, barrier, one way to use barrier is to time measurement, because every barrier command will make your program be slower than without barrier. And if your program works just when you use barrier, that means your program have some errors, logical errors, because barrier slow down your program, and that means somehow this helps to run your program correctly. But if without barrier it works non-correctly, gives you wrong answer, that means something wrong with your program. Do not solve your problems using barrier, because when, for example, you maybe you take your program and launch this program on other cluster, maybe which is will be faster than our. Maybe even with barrier, will be wrong answer. So you have to find this error, logical maybe error, and to solve it without barrier. So barrier used just with the time measurement, because time measurement you check. There are two checkpoints with the same time level with barrier, in the very beginning and in the very end of your program. Because when other processes will know some information from other process, from one process. Okay. Scatter, you divide one array and
and send chunks.
Send chunks, yes, and bricks, chunks to other processes, and every process will receive its chunk. Gather the same, but vice versa. Some process collect these chunks from other processes, and reduce some collective operations on the elements which are elements of the arrays which are on different processes, and so on. All reduce, this answer will be in all processes. Okay, so 3 minutes. Okay, answers?
Thank you, sir.
No? Questions? No? No questions?
No questions, sir.
Okay. So, okay, see you next time.
See you next time. Bye-bye.
Bye.